Hello and welcome to day 2 of our first steps with Geant4 course. Thank you for joining us either in person or remotely. I'll hand over to Alvaro now, who will start with a recap of what we did yesterday.
Thank you very much. Can you hear me? Also in remote?
Loud and clear.
Okay. Thank you very much. So thank you very much for coming today too. So as a recap, what we did yesterday was we started by a general review of what Geant4 can do, what Geant4 is, what Geant4 cannot do. If you remember a bit, Geant4 is, I will repeat it again, and I will repeat it many times along the course. It's just a software toolkit. The Geant4 does not provide an application that we use to simulate using Monte Carlo algorithm the passage of particles through matter. That is, in essence, what Geant4 is. Then we did a review of how to install Geant4 and what are the main features. The minimal requirements for Geant4, if you remember, in addition to the source code, is just C++ compiler and the configuration tool CMake. But if you want other features, for example, some visualization, some ways of visualizing the geometry or the events, you need to install some libraries. For example, in our case, in the virtual machine, we are using the Qt graphical interface plus the OpenGL visualization driver. So those must be installed before installing Geant4. Then we reviewed a bit of C++, and we started using some of the Geant4 components. We started by simply using G4 double, which is just an alias of a double in C++. Then, if you remember, we used the method G4 cout to print out in the terminal some messages. And we end up this warm-up in C++ by reviewing the concepts of interface in C++, in particular via implementation of an abstract class method, which is the keystone of the Geant4 toolkit. Then we reviewed with a presentation how to build materials, which is the most basic component of the geometry, as we will see. We can use different levels of detail. We can simply implement the material and let Geant4 guess the element and the isotopic composition. But we can also build up a material by mixing different elements. We can build up a material from other materials, from a mix of other materials. And similarly, we can even specify the certain isotopic composition of a certain element. And answering a question that was happening yesterday, yes, Geant4 offers the possibility of defining the same element several times with different isotopical composition. And then you can use this element in different materials as you wish. Today, we will finish the material section by reviewing the Geant4 NIST material database, which is just a collection of predefined Geant4 materials whose properties are taken from the data evaluation made by NIST. And we will see what is the difference and commonalities between using this way of getting materials or finding those by yourself. Then we will continue with the materials is one side of the description of our experimental setup. The other side is the geometry. So we will review the geometry model that Geant4 offers for us. It's our responsibility to create our geometry description of our setup. And finally, hopefully today, before the break, we will implement our detector construction. So we will define our materials, our geometry, and everything encapsulated using the Geant4 interface to do so. On the second part of today, we will review what is a physics list in Geant4, this object that will register the particles that can be used or may appear during the simulation are their physical processes that will describe their interaction with the materials in the experimental setup. And I think with that, I have covered the recap from yesterday and our plan for today. Is there any question about that? Okay. So before I start, with a recap of materials and implementing the NIST materials by coding, I wanted to advertise that at the end of each day, I will upload the code as it was in my virtual machine to the Indigo webpage. And if, for example, you go to the timetable for Monday and you go here to preliminaries and you click on the clip, you will see that there is a file called endoftheday1.zip. If you open it, you will find 4 directories plus a README. The README will contain information about what we were coding yesterday. So the 4 directories are the copy of the basic V1 example taken from the installation directory, the build directory, as we did just afterwards to test the installation, a subdirectory called intro to CPP, to C++, where we have, I think I deleted the first step. So only the interface example exists in that piece of code. So in that example, you will see how the code looks like when using an interface that I call the solid to define an interface method called getVolume, and how 2 different shapes that derive from this one, cube and sphere, use that, and how that simplifies a function called printVolume. So you can take a sphere, a cube, or whatever other class that derives from solid, and it will be able to use this interface method getVolume. This it was just a very simple example to show you how interfaces could be implemented, and we will see later how this is used in geometry, because this is a simplified example of what Geant4 actually does. And in the 4th directory, we have intro to Geant4, where we saw different ways of creating isotopes, elements, as letting Geant4 guess what is the natural composition, the isotopic composition, or specifying our own, and using those to create new materials. Now we will finish this example by showing how to use the NIST materials from Geant4. Everything clear so far? Okay, so we will move to a short recap. So as I said, to describe our experimental setup, we need materials and we need a geometry. Yesterday, we were reviewing the material model. Geant4 allows you to define the material composition at different levels. We can define the isotopes, we can define elements, or we can simply go ask Geant4, please define a material which will correspond to a pure element by simply specifying the atomic number, and Geant4 will guess the rest. The important idea to keep in mind is what information each object will retain. So isotopes will be attached to nuclear properties, elements will be attached to atomic properties, and elements will have these macroscopic properties such as density, temperature, pressure, or state, which are the last ones optional. This was the way we used yesterday to implement the material. In particular, an element. In the first case that you see here, it's by simply letting Geant4 guess. On the bottom part, we saw how to specify the isotopic composition. Similarly, for a material, in this example, you see how to let Geant4 guess what is the composition of the element composition. In this case, is a pure element, which will be identified by set 92, which corresponds to uranium. But we can also specify the different elements that make up a material. For example, here you see how to implement the material H2O, water, by specifying the elements. First, we specify the element hydrogen, then the element oxygen, and finally the material water as made of these 2 elements in this stoichiometric ratio. We can also specify the composition of a material by mass fraction, also by elements, or by mixing elements and materials. In this case, for example, aerogel material is very complex and is made of another 2 materials, silica and water, but also the element carbon. And at the end, Geant4 will reduce all of these into a mix of atoms in order to calculate some of the properties needed by the physics. Okay. Sí.
1 second.
So in the end, the variable set is a double, but it's the number of protons, I guess. So
yes. So for historical reasons, when defining an element, the atomic number was defined as an effective atomic number. Nowadays, if you try to use a fractional number, because this is still a double, so you can still say instead for oxygen, you can still say instead of 8.1, Geant4 will trigger a fatal exception and will not allow you to run. So the interface didn't change, but a protection was added later. So the atomic number is still double, could be still fractional, but actually, if you try to use a fractional number, a non-integer number, Geant4 will not allow you to run. Thank you. So with this, we have reviewed different levels of detail that Geant4 offers to define materials. However, as long as you can, please use the Geant4 NIST material database, because this will ensure reproducibility and some of the properties that will be attached to the materials will be more accurate than if you let Geant4 build the material step by step with all these levels of granularity. Of course, if you have to do it because you are dealing with an isotopic enriched material or something like that, you will have to do it by yourself, but you have to be aware that some of the properties of that material might be different than the ones that the Geant4 NIST material database will offer. So in order to access, the important part here is that the NIST, this database can be accessed with this syntax that you have here in red. We can either find or build an element. We can find or build an element by symbol or by atomic number. Or we can directly call for materials, which is not here. This database contains more than 300 materials at the moment, but might be expanded at any moment. The materials include all the stable elements and some of the most used compound materials, for example, air, aluminum oxide, or others. Some of these materials are widely used in nuclear, high energy physics, but also in other areas. For example, in space science, we have Kevlar or neoprene, and also some materials used in biochemistry, for example, the DNA bases. In order to build a material, instead of find or build element, we use the interface very similar, find or build material. And this is the way we would use it later on. Okay. How do we know if an element or a material is implemented in Geant4? Well, we can print this list of elements and materials. And also, if you go to and we will go together to the user guide for application development, there is an appendix with all the elements and materials. And I think we will see later also some of the properties. So in our application, also I will do a recap on that. We will use simply the NIST manager to keep it simple. Good. Any questions so far? This was just a recap from yesterday. Okay. So now we will go back to coding. We will finish the example by now using the NIST. We will implement some materials coming from this database, and then we will go back to the presentation to review the geometry model. So now I will start sharing from my laptop. Okay. Okay, let's see. Good. So the first thing we will do is to review the documentation regarding this Geant4 NIST material database. So we can go to the main Geant4 webpage. We go to the documentation, and as you see here, we have several user guides. The first one is for application developers. Here on the left, you have the menu. You can see the different categories. We will go to appendix. And the first section in appendix is actually the Geant4 material database. So we can go to NIST compounds, for example, and here you will see the output of the command that we saw on the last slide when printing the list of all the materials. You have also all the elements listed here with some of their properties, particularly the density, and I believe this is the mean ionization potential, mean ionization energy. If before implementing your own material in Geant4, please check this list. And I guess also you can always make a request to Geant4 to implement a material if it is useful for the community. Okay. Now we can go back to the test, to the code, sorry. We will use the terminal again to navigate the directories and open the editor again. So we are in this home local one, the main local user of this machine directory. We created yesterday a directory called work here. We can navigate, we can move into this directory by typing cd space work. We can list again the content by using the ls command. You will see here all the directories and the zip file that I sent you by Mattermost and posted in the table. We can now cd into the intro to Geant4, so we will continue the development of this file. And we will use gedit to open our application.cc file. And if you put an ampersand at the end of the line, the terminal will remain free for you to use to compile this file later. Okay, good. So if you open the end of day one.zip file, you will find this. If you want to continue from your files, it's also fine. Every day I will start from this end of day x.zip file that I will upload at the end of each day. So if you get lost, you can always continue from that instead of from your local work. So if we want to use a new class, what is always the first step we have to do? We have to include the corresponding header file here on the top. So we go to the top and type include Geant4 NIST manager.hh. Okay, now we go to the bottom and we can continue the development here. So we can put maybe some comments just to make it a bit more readable.
Can you show the name of the class again?
Yes. So it's the name of the class is Geant4 NIST manager. In Geant4, there is this consistency between the name of the class and the name of the header file. So if the name of the class is Geant4 NIST manager, the name of the header file, unless there is a terrible mistake we didn't notice, it should be Geant4 NIST manager.h. And we will follow the same prescription for our application because this keeps everything consistent. Okay, so this will be an example of using the Geant4 NIST material database. We can start by typing this. So G4 NIST material asterisk, because it will be a pointer, NIST equal G4 NIST manager dot instance. This will retrieve the class. This is a singleton, so there should be only one per application. In case that does not exist, this method instance will create one for us. The important thing is that it will return a pointer to the Geant4 NIST material database. Now we can do as we did in the example. So we can retrieve elements from NIST database, and we can do, for example, we are going to make the water material, but out of the elements of the NIST. So G4 element H equal NIST find or build element, and we will use, for example, the chemical symbol. We can do again for oxygen. So G4 element asterisk L oxygen equal NIST find or build element. Watch out with the capitals that of the method. The F, the O, the B, E are capital. Okay. And now we build the water material out of these elements that we retrieve from the NIST. We have to provide a density, so we can say the density of water is 1 multiplied by the units, CL Hep gram divided by CL Hep cubic centimeters. Okay. And we also have to specify how many components have the water. So we will use the stoichiometry way. So we will give the ratio of atoms. So we have to say that it has 2 components. Yes? Yes. So if that is a way that it is possible in C++ to get rid of the namespaces. So this CLHEP dot is, so the question was if we can get rid of CLHEP. Yes. So the answer is yes, but it's a bad practice in general and can lead to terrible errors. Why? Because we could say something like that. You don't have to do this. If we write this inside our function, the compiler will know that we are using gram G as from CLHEP. The problem is nothing prevents you from doing this. And now you will have, in best case scenario, an error, worst case scenario, a bomb. So yes, you can use these aliases if, for example, you are using grams inside a function many times, but it's better to not remove namespaces. For example, you can do this, but this is terrible. If you do this, you will be removing CLHEP from every class bit from CLHEP, which means units, constants, everything will be removed. You don't need to type it, but that can create collisions. And debugging these kind of errors can take a very long time and effort. So better not doing it. You can also do this and load the whole STD space. But again, this is a bomb that you should avoid. This is bad practice in general. Yes, please. I will repeat the question, John. I can repeat the question if needed. Okay.
Yeah, I would just say that. Okay. Is the 58th line correct? As in NIST manager or NIST material?
Don't worry, the compiler will help us find problems. Some problems are by mistake, some problems may be on purpose to keep us sharp and awake.
Thank you. That was not intended, but thank you very much. Yes. I have to say that some of the errors are intended, but not all of them. Thank you very much. Yes.
We're making sure that everyone stays awake.
Thank you.
Concerning the units, I mean, there is also a header in Geant4 that allows to bring all the units into the global namespace. Okay, so there is, it's called G4 system of units.hh.
Yes.
I mean, you can use that, so you will have all the units available, and you can avoid to put the clab ... in front. But it is you have to use that with care, in the sense that you can use that in the source code, but not in the header files, because if you will use it in the header files, you mean that you will bring all the symbols in that file in the global namespace, and that can cause problems of duplication of variables that may be set with the same name. Okay, so it's something that you should use with care, but you can do it.
Thank you for the note. So please, in summary, keep the namespace. Someone put an effort writing a namespace, please respect it. So yeah, so we have defined the elements for the water. We have to provide the constructor of G4 material, a density, and the number of components. So now we can say my water equals new Geant4 material, and we have to pass all the arguments that maybe you remember from yesterday. We will have to pass a name. So we will say my water, because it's not one that we are building from scratch, almost. We have to pass the density of the water that we are building and the number of components. Excellent. So now, if you remember, G4 material allows to redirect the properties to the G4 cout. So we can do G4 cout, redirect my water, redirect G4, end of line. Now, with this, we have built G4 material out of the NIST database for elements, but we can also use the NIST material for water. All the materials and elements in the NIST database have a name that starts with G4 underscore and the name of the element or the material. Ah, yes, yes, of course. Yes, good point. It's always better to cross-check. So back in the terminal, we can change directory to the build directory by typing cd space build, and we can type make to build again the executable. Yes, so I made a mistake because I forgot to put the asterisk that identify my water as a pointer to a G4 material rather than a material by itself. Yes. Ah. Yes, sorry. Okay. So the error of the compiler is conversion from G4 material to asterisk to G4 material requested but not possible. It means that it is trying to assign a pointer, a memory address, to an object that is not a pointer. To solve the problem, we only have to say that my water is an actual pointer. We save, and we go back here. And now it compiles. We can execute by typing / or application. I hope it fits. Okay. Very good. We forgot to put the elements. So we have to say add element using the stoichiometric ratio. So how many hydrogen atoms there are in a molecule? 2. And we can use, we can use the add element to add each 1. Okay. I will try to keep it open. Sorry. We can go back to the terminal and type make to recompile and execute. And now there is no segmentation fault. And we see that there is a new material called MyWater with the density that we specify, with other properties that are not of interest right now, and is made of elements with this mass fraction and isotopic composition. Very good. Now, we can, this is still a bit cumbersome, and hopefully you don't have to do it for every material that you might need in a Geant4 application. So we can show how to retrieve a material directly from Geant4 NIST database. To do so, we can say G4 material asterisk, because it will be a pointer to a G4 material, NIST water equals NIST, which is a pointer to the G4 NIST manager, find or build material before we use find or build element. And here we have to provide a name. Every name will start with the prefix G4 underscore, and we have to specify the name, usually in capital letters. Now we can also print it out. By using the same method as before. So G4 cout redirect NIST water redirect G4 NDL. We can save the file and we can go back to the terminal. We can do make again. Yes, so the prefix of every material in the Geant4 NIST material database will start with G4 water. G4 underscore and name of the material. And you can check the available materials in the appendix of the user guide for application developers. Now, if we run the application again, did I recompile? Yes, sorry, my bad. I interchanged the print outs. Sorry, it's a bit confusing. Okay, so before we had this material, MyWater, with all these properties. Now we have G4 underscore water with this formula and all these properties. If you check number by number, you will see that all the numbers, almost all the numbers are the same, and the composition is also the same. There are some properties that are hidden from us, but are used by some physical processes. When you build a Geant4 material out of the elements, Geant4 will use some recipe to calculate some of these properties that are hidden from us. You can still change them and access them, but we are not touching them now. If you use a material from the NIST database, those properties will be taken from the experimental data. So it's always preferable. In summary, the takeaway message is to use the Geant4 NIST material database. Any questions so far? Okay, we can do one last thing. That is to create dummy material or try to access a dummy material. So we can type G4 material Philosopher's Stone equal NIST find or build material G4 philosopher's stone. Okay. Sorry for the long name. And we can try to print it. G4 cout philosopher's stone redirect G4 NDL. Now, what do you think it will happen if we ask Geant4 NIST database for a material that does not exist? We will see. So we can make, we can run, and it will explode. And the reason is that this pointer, this philosopher's stone pointer to a G4 material is null. When the NIST database is asked for a material that does not exist, is not contained in its database, it will return a null pointer. So if we want to protect our code against null pointers, and you should always do that whenever you are dealing with a framework, you should always put an if statement, if null pointer different from philosopher's stone, then do something. Otherwise, what we have to do is to say material not found. Okay. Sometimes you cannot know in advance if something will be null. So before using it, in our case, the use was very simple. We only wanted to print it out. You have to cross-check if a pointer is always null or not. Good. Any questions so far? Yes.
Are there any other databases that maybe not including the Geant4?
I mean, are there any other databases than the NIST database? Maybe not included with Geant4, but maybe other people add on top.
I don't think so.
Okay.
Maybe Gabriele, do you know? You're aware of?
Well, there may be, yes, but that's what you use. I mean, that's it's fairly complete. So
Good. Thank you for the question. So if there are no more questions, with this, we end up the introduction to C++, and we can actually start the development of an application. To do so, we are going to go one level up. We can also close the text editor. We can go one level up twice. We will arrive to the work directory, and we can create a directory called with mkdir command, mkdir space intermediate application. Okay. We can copy the CMake list that we were using in the intro to Geant4 by using cp space intro to Geant4 / CMake list to this intermediate application directory. And we can change directory to intermediate application. So now what we should have is a directory called intermediate application with only a CMake list.txt. We will start. We can use the command touch just to create an empty file. We can create an empty file called O application by writing touch space or application.cc. This will create an empty file. We can create the subdirectories include and source. The first one will contain the header files of our classes, and the second one, the source. And I just realized that I ran too much. Sorry. Before this, we should review the geometry model of Geant4, because otherwise you might be a bit lost. Okay. Sorry, I tried to run too much. Good. And, okay. Sorry. So we will review quickly the geometry model of Geant4 before implementing our own application. Sorry, I forgot. Geant4 geometry model is made in 3 layers, in 3 conceptual layers: the solid, logical, and the physical volume. Don't worry about the names, because maybe now they are not very meaningful to you. We will have to create these objects by ourselves using new, but when creating these objects, they will be self-registered in a corresponding store, so-called like that. It's a container. So for solids, we have the G4 solid store, and the same for logical volumes and physical volumes. So Geant4 kernel will take care of the memory deallocation whenever it is needed. The geometry description can be rather complex. As I was introducing the geometry yesterday, we can describe our experimental setup or this room in a hierarchical manner. We can say, okay, I want a volume of that represents this room. Inside this room, we will place components, tables, chair, or shelves, computers. Inside a computer, we will have another pieces. So in this manner, we can create a hierarchical geometry description. And of course, each shape will be attached to a material. We will start by so there are 3 conceptual layers. We will start by reviewing the solid. Solid represents a shape in Geant4 and is derived from the G4B solid base class that provides an interface to compute distances between the shape and any given point, check if a point is inside or outside, and to compute the surface normal to the shape at any given point. So we know that all the shapes in Geant4, sorry, can someone open the door, please? So we know that every solid in Geant4 will implement these methods. How each solid implements it, it's not important for Geant4. It doesn't matter if it is a cube or a sphere. The important thing is that the cube or box that we will be using in Geant4 has all these methods. A cube in Geant4 will be able to compute the distance between any point and the shape, the surface normal at any given point, and so on. These shapes will be described by a minimal set of parameters, and all the shapes in Geant4 derive from this G4B solid base class. We can review now the documentation or the source code, as you prefer. So we go to the user guide for application developers. We can go to detector definition and response. You have different sections here. We are in geometry, and in particular, we want to check solids. So here you will have more details about the different solids in Geant4. Geant4 implements more than 100 solids, including all the second order surface solids. At the beginning, for us, will be enough to use a box. The box will be constructed from the class G4 box and will take as arguments a name and half the size on each direction. Keep in mind that we have to provide units. Here, you have an example how to do it. And this is how we will be doing shortly. Okay. Now, the next conceptual layer of the geometry model of Geant4 is the so-called logical volume. Logical volume is simply 2 things: a pointer to a material and a pointer to a mathematical shape. it will contain all the information of the detector volume except its placement in a space or its dependency with respect to other solids. This class, as you noticed, then is simply G4 and the name of the class. There is no V afterwards. It means that it is not virtual. It is an actual constructor. In addition to the material and the mathematical shape, the solid, the Geant4 solid, this logical volume can be attached to a field manager. So you can define a custom magnetic, electric, or electromagnetic field inside this volume. And you can also instrument it with some physical limits that might be used during the simulation itself. And here on the slide, you have the constructor as it is in the source code. So I will not go to the source code. And on the bottom side of the slide, you have an example of what we'll be doing shortly. We have to provide a pointer to the mathematical solid. We have to create in a previous step to the material and a name. As from a experience point of view, from practice point of view, you can, Geant4 allows you to define solids and logical volumes with the same name. You can always say the box, the G4 box will be called target, and the corresponding logical volume that will point to that solid will be called target 2. However, this can be a bad practice. So you should be verbose when naming objects too. It's better to say target solid or target logical volume, at least with a letter to make a difference in case you do a search based on its name. Yes, so thank you very much. So the question was if I can repeat the use of user limits. So user limits is a collection of limits or limitations that can be applied during the tracking, for example, and that can be applied per particle. So these limits will be used not during the geometry construction, but later during the simulation. And a typical use case can be to limit the size of a step during the simulation. For example, you can say, no, I want these particles to have smaller steps, so you can force more interactions inside this volume. You can go to the documentation and cross-check what are the different user limits and their use case and how to implement them. We will not tackle this in this course, but I'm sure it is further explained in the advanced course that will happen in autumn. Thank you for the questions. So we said there are three conceptual layers: the solid, which represents just the mathematical shape, the logical volume that encapsulates this shape plus the material, and finally the physical volume. So a G4V physical volume is an abstract class that represents a physically positioned volume. You had a logical volume. For example, I have the volume table, logical volume table, and I want to place it inside the room. So I have to say, okay, this table will be placed inside the room with respect to its center at a given distance. Maybe it will be rotated. This will be called, this is the method that we will be using, called simply placement. So it's one position volume, and it will be used as we will see later. But there are other ways to place volumes. For example, by repeating volumes. It happens in detectors that there are some symmetries, and those can be exploited. And Geant4 offers different mechanisms to exploit this symmetry by using either replica or parameterized volumes that allows you to place volumes, multiple copies, or to make even divisions too. In our case, as I said, we will be using a type of placed of a physical volume, which is called G4 physical volume placement, PV placement, that represents one placement of a logical volume. It is created by associating a logical volume, for example, a table, with a transformation in a space that represents a distance from the mother volume center and a rotation, which is optional. The mother volume should be specified for every placement, except for the most top volume. For example, if our experimental setup is inside this room, when implementing this in Geant4, when defining the room volume, placed volume, we don't have to specify any model because it will be the topest. Any other placed volume will be placed inside the room volume or any other daughter volume. Yes?
Will there be an issue if I accidentally have two volumes for which I have no mother volume? So no clearly defined groups?
Yeah, so the question was, what happens if I have two topest volumes? I believe the Geant4 does not allow to define two world volumes.
It's not a problem. One of them cannot be your world volume and will never appear in what you're simulating.
But we don't know which one.
No, you tell it. You're going to tell it which is the world volume. You will tell it later on what's the world
All
volume.
the simulation will happen inside the world, the topest volume. And one of the, I was talking yesterday about the end of tracking conditions. One of them will be go beyond this volume. If a particle tries to get out of the mother volume, it will be killed by this condition. And it means that if you inject a primary particle in one of the worlds, it cannot jump into the other one. Thank you. Okay, and so these are the three conceptual layers of a geometry model of Geant4. And this last slide is just for the future because it will not, we will implement it today, but we will not use it today. We will define our geometry and materials in this in a function, in a method of or derived class called construct. But if we want to change it between runs, it is possible, but we have to notify about these changes to the run manager. If we remember yesterday, the run manager is the only manager that we have to define in our application, and it can be as a director of orchestra for Geant4. We will register there the detector construction, we will register into the run manager the physics, and all the user actions, including the primary particle generation. If once we have initialized the geometry and the physics, we decide for some reason to change the geometry or the materials, we have to notify this run manager. And to do so, we have to use these methods that are on the bottom part of the slide. In case we have changed placement, we can use geometry has been modified. So the construct method will not be invoked. It means that no new volumes will be created, no new materials will be created, simply some optimization that is applied after or construction of the geometry will be redone. And reinitialize geometry will, if I don't remember now if there is an argument there, it will call again the construct method. It means that it will call again, it will construct all the solid, the logical volume, the place volumes, and the materials that we are creating inside this method. And we have to call this method in case we want to change the geometry between runs or once we have initialized the run manager. Similarly, if we change the materials that we are using, for example, if we want to change the material of which our target solid is made of, we have to also notify the run manager, but using a different in a different function called physics has been modified. This will tell the physics list, watch out because there might be a different material. So in case you need to recalculate some properties or reduce some tables, please be aware of it. And the physics list will take care of that. Any questions so far? Okay. So now for real, we can start implementing our application as in the point where we left. Okay. Sorry for running too fast. Okay. So to recap, we have created a new directory called intermediate application. We are in directory work / intermediate application. We have copied the CMake list from our previous project, Intro to C++, by using this command, cp space if we are doing it from this directory, we will need to do it like this. Okay. cp space dot slash intro to Geant4 slash CMake list .txt space dot. So the file will be copied locally. Okay, now we can use the command touch to initialize an empty file called or application.cc. We could have copied the previous file too. And we can create an include and source directory by doing like this. Okay, now it complains because the directories already exist. Good. We can open the Gedit editor and we can open our application. We can type main. At the moment, there will be nothing. And we will include already a header that we will be creating shortly. Okay. There is not much here. We can close it and we can now create or include the file your detector construction.hh. And we can put an ampersand at the end to keep the terminal free. Good. This will be our first serious class that we will be defining today. So we should, maybe by courtesy, we can specify the name of the file. Okay. Now we will type this. We will type hash if and def your detector construction underscore hh, new line hash define your detector construction underscore hh, new line hash endif. This is a preprocessor macro, and it will make visible the code to the compiler only if the preprocessor variable macro your detector construction underscore hh has not been defined yet. This is something that you will see in every class of Geant4, around every class of Geant4, and it will protect against several inclusions. If your header is included 2 times inside the same translation unit, inside the same file, the second time you include it, because this preprocessor variable macro will be already defined, the second time will not make the code visible. Otherwise, you will have a compiler error because you try to define the same class twice, because in case it was included twice. Okay, now we can define the class. As I said before, it's a good practice to use consistent naming all over the place. So we will call our class your detector construction, and we will be using the interface method provided by Geant4 to implement a geometry. And we will use the same syntax we saw yesterday for the solid. In our case, the public interface is called G4B user detector construction. Sorry for the long name. And watch out with the capitals because they are very misleading. Very error prone. Okay, we can open and close curly braces. This is a class we will be using, so we need to include a header for this. And now, since this is an interface, we have to implement the interface methods. The only interface method of this class will be the method construct. We can cross-check it by going to the source code. Okay, we will open. There are many ways to access the code. So I will go to the install directory, user, local, Geant4, include Geant4, and now we have to look for this class. G4 user detector construction. So this is the header file that will be actually loading. This is the header that was installed, and this is the header file that you can also see in the source code, either from the GitHub, the Doxygen. We will see different sources. And here at the very beginning, we have the definition of the class, G4 user detector construction. We see that they are taking the default constructor and destructor very well. And now we have this. This is exactly what we saw yesterday with the function, the method, the interface method get volume of the solid. This equals 0 means that there is no implementation. And if you derive from this class, you have to implement a construct method. In this implementation is where we will describe our geometry for Geant4. So now we can go back to our class. We can create a constructor. At the moment, it will not do much. We have to create a destructor with tilde, the name of the class, and parentheses. As you noticed, the destructor of the base class is virtual, so we have to mark it as override. This will not change the logic, but it will prevent any errors in the future. In addition, we have to override the construct method. To do so, well, we can go back to the definition. You see that it's virtual. This method will return a G4 physical volume pointer. So we can copy this. We can type it here. G4 physical volume asterisk construct. And because this is a derived class, again, we are overriding a method from the base class. We have to mark it as override. Good. Now, if you remember from the introduction yesterday, our geometry will be extremely simple. It will consist only in a box of a given material placed inside a bigger box that will represent our wall. And ideally, we will like to change to determine by ourselves the material of which this box, the target, the smaller box is made of, and its thickness. So we can assign those as properties of our class. So we can define some private members. For example, a G4 material. And a G4 double that can be target thickness. The idea of the application that we will run is, or the final goal at the end of the week, is to run a simulation of particles that are being shot to this block of material. They will interact somehow, they might deposit some energy, and we should be able to extract some information, in particular the energy deposited by all the particles, the primary and the subsequent secondaries, inside this target. And for later, you will see why later. We will also implement a physical volume pointer that will be filled later to our target physical volume. I forgot to mark the methods as public. By default, if in a class, methods and members will be private unless you say otherwise. When all the methods and members that we define, we declare after the public keyword will be accessible by other classes. The members and methods declared after the private keyword will be only accessible within the class by any object. It means that between objects of the same class, they can see these members or methods, but those cannot be seen from objects of other classes. Good. So usually it's a good practice once you define a member of a class to define also setters and getters. In our case, we will define setter and getter for the target material and a setter and getter for the target thickness. We can start by the getters. And in this case, the getter will be naive, so we can implement it in line. We can also implement the getter get target thickness. And again, we can implement it in line, return a target thickness. We can also implement the setters. Sorry, declare them. The implementation will go somewhere else. Okay, so these are the typical declaration of getters. The getters will be functions, methods of the class that will return either a const pointer to the value that we are dealing with, or a copy of the value, as in the second case, of the certain property. In the first case of the material of the target, and in the second, the thickness. For the setters, is the other way around. These functions will not return anything. They are marked as void. They will return void, nothing. And we'll take as argument, in the first case, for the material, we will set the material by name, because we will be using the NIST manager to retrieve the material from the NIST database. And in case of the target thickness, we will pass a double by copy. Good. So far, so good? Okay. We can try to compile this code and see what happens. Do you think it will work or it will not work? We have to create a build directory. If you remember from yesterday, we will be using the same. So cmake s -s capital S dot, because the source code is at the same level in the same directory where we are, space -capital V build, for example. So this will configure the project. I will try to go up. So this is the command that we have been using. Okay. Now we can move inside the build directory. And now let's see what happens. Okay. So we have only one error here, which says G4 material does not name a type. Do you remember this error? What we were missing? Sorry? Include. Very good. We are missing the include. The compiler do not know what is this G4 material class that we are talking about. So one naively could think about doing something like this. You don't need to do it. And this will make the code to work. However, whenever it is possible, please don't include headers in a header file. Since we are dealing just with pointers, we can simply say there will be a class called G4 material. This is something that is called forward declaration. And in the source implementation is where we will include the header, but not here. There are some advantages that we will see later on Thursday on the course. This is just a promise to the compiler that there will be a class named like this. But the compiler do not have to know at the moment what this class is doing. If, for example, we go to the header again to the G4V user detector construction.hh provided by Geant4, we will see that they do it for many classes here. So they are doing a forward declaration for the class G4V physical volume. They are doing it for logical volume, parallel world, many other classes that we don't need to know. And you see that this is a practice that will be found all over the toolkit. Good. So now with this promise to the compiler that the class G4 material will exist, we can go back to the terminal.
From where does the file then know G4 material and so on? Is this then just imported by G4 user detector construction?
So G4 material is not declared at the moment. We could write hash include between quotes G4 material.hh, and in such a manner, we will include the whole header of G4 material class into our project at this point in the header. But there are several disadvantages of doing that. So it's good practice to use this method of forward declaration, simply telling the compiler, just for you to know, there will be a class called G4 material. At the moment, this is enough because we are only dealing with pointers. In principle, you should only include the headers if you are using the classes. For example, if you are deriving your class from G4V user detector construction, yes, you are forced to include this header, the corresponding header. But if in this header we are not using G4 material for anything except for declaring a pointer, we don't need to include the corresponding header.
But then what about G4 string and G4 double? Where did they come from? Globals.
From globals.
Yeah, did we import that?
No, but G4V user detector construction is doing it.
Okay. Got it.
Yes. And if you see, for example, G4V user detector construction is also importing the vector STL container and also declaring several forward declarations. This is something that you might see across the toolkit. Sometimes by including one header, this header will include inside other headers, and magically sometimes you don't need to include some. Thank you for your question. So the question was why we don't have to include the corresponding header for G4 string, and it's because it's included in globals, which is inside the G4V user detector construction.hh. Okay, so we can go back to build, and now it builds. It's not doing great, it's not doing much, but at least the code is injected into the source code that is being compiled into our application, which is empty at the moment. It's not doing anything, but we know that it runs. Good. So if you agree, John and Gabriele, we could maybe stop here and implement the detector construction after the break.
Yes, I think that makes a lot of sense.
So is there any question, or otherwise we can go for a break?
1 second, let's catch any questions. I will also mention for people who are remote, I will try and do a Mattermost poll about whether people are following, but whether it's a bit too fast, whether it's far too fast, whether people are following well on Mattermost. People inside the hall can also join.
It's not a question.
Oh, sorry. Okay, sorry. Okay, any questions online? If not, let's break for 30 minutes and rejoin at 1:45. Give us a bit of learning from yesterday. 25 minutes was not quite enough.
Yes.
If you want to give feedback about whether we're going at exactly the right pace, a little bit too slow, a little bit too fast, or you're both, it's far too easy or far too difficult, please join the Mattermost channel. I'll try and put up some information about it if you don't have it, or look in your bulletin.
Thank you. So we will reconvene in half an hour. Thank you.